Okay, sorry for the delay, everyone. We had, as always, a crazy week, but we realized we had a lecture to do to the Australian Wood Council. There was about 500 people worldwide that signed up to watch it. And we were like, it's too bad we can't give this talk to the students. And since we were behind, let's be honest, we figured, you know what, it's probably actually the perfect talk to give. It's almost always exposed. Not always. We'll show you some circumstances where it's not. But it really is structure that becomes architecture. So we thought reciprocal frames, great talk to give to the students. So lecture 6, reciprocal frames. So because this is built off of another lecture, it's not going to follow the exact same format as some of the others. We're going to talk about what they are, why we build them, has it been done before, is it worth it, and then we're going to show you a bunch of examples. Some that we've done, some that other people have done.
So when I think of a reciprocal frame, I always think of this image from the Lorax and this quote. He lifted himself by the seat of his pants, and I'll never forget the grim look on his face as he hoisted himself and took leave of this place. The reciprocal frame is a little bit like that. It's one of these impossible things. Of course, you can't lift yourself by the seat of your pants, and yet when you look at a reciprocal frame, it kind of feels like that's what's happening.
So what is a reciprocal frame?
A reciprocal frame is a structure made up of mutually supporting beams in a closed circuit. This is a quote from this great book by Olga Popovic-Larsen on reciprocal frame architecture. The classic example of a reciprocal frame that we would be familiar with is this fireman's chair. You get the four hands interlinked, and we can span with our arms carrying heavy load and no moment connections, which essentially means not a great deal of muscle power.
And as we all remember, moment connections are hard to do, which would be hard with hands, but in a building they're expensive, hard to build on site, so we try to avoid moment connections as much as we possibly can.
So what is a reciprocal frame? We have all done a reciprocal frame. One-dimensional reciprocal frame is simply two lapped boards. You can see that neither one of these boards goes all the way from support to support, but we lap them and connect them together, and they mutually rely on each other to span.
I guarantee if some of you are building your model out of popsicle sticks and you didn't have popsicle sticks long enough to make the member you wanted, you did this. Instead of nails at each end, you probably did glue. But you've probably done this even in your model, or probably half of you have done something like this in your model.
So what happens if we extrapolate from that one dimension into 2 dimensions? We take those two lapped boards, we move them apart relative to each other, and then we introduce 2 perpendicular boards with 2 additional supports, and now we have a reciprocal frame. What's interesting is that each of these beams carries 100% of the load of one beam on one end. So look at any one given beam. Obviously, we have 4 beams carrying 4 beam loads. We have 4 columns. Therefore, each column carries 100% of the beam load. We have 100% of the reaction of that beam carried at one end. This is as opposed to a typical span, where we would have 2 supports and a beam, and each support would carry 50% of the beam load.
So why the heck would we bother to do a reciprocal frame? What can we get out of it? Folly. I mean, folly might not always be the best reason, but sometimes it's a darn good reason.
In architecture school, they call that formal.
Span is a good reason. We want to make longer spans with short members. Two-way action and geometric complexity. So we'll just take a look at a few of those things. Before we do that, let's talk about what goes into cost and what we have in our head as a perception of what cost is related to. And we're always taught that efficiency, or engineers are taught that efficiency is the best solution. And making repeated elements again and again, make the same element as many times as you can and get that in there.
So efficiency comes down to three things, or apparent efficiency comes down to three things. It comes down to repetition. You need the same member, so that not every member is unique. We need to minimize piece count, and we need to minimize volume or tonnage of material. We want to show you that it's possible that more complex can be cheaper.
I like to talk about this in relation to gold ring, for example, the gold ring center for
coffee,
high performance sports at U of T. That was a project where very early in the project it became essentially a design build project, and the contractor had it in their head that getting steel tonnage down was the answer. We kept saying it's a complex building. To get tonnage down, we have to add complexity to connections. So every time we take a little bit of tonnage out of the main members, we're putting that somewhere else. Because it's a complex building, that goes somewhere else. And putting the complexity into the connections what am I trying to say?
Well, one thing you're trying to say is that when every member is different, things are more complex, but your tonnage goes up. If you want to minimize your tonnage, you optimize every single member, but then they're all different throughout the building.
Thank you. I got halfway into my story and
you're obsessing with my coffee.
I don't know why. I'm very confused this morning. I need more coffee, but this is your section. You wrote this, and I don't.
Why don't I just finish this section?
Yeah.
Okay, so this is the complexity curve. Well, I have to admit that I didn't review this slide beforehand either. But
some of this was a lecture we gave because we've given a version of this like 3 years ago, but the lecture we gave on Monday was only 40 minutes. We had to cut out a bunch of stuff, and so some of these slides. I kind of merged both lectures about 10 minutes ago, and neither of us have looked at it. So if we're tumbling over stuff, we're expecting the slides to be in the order we practiced for on Monday, and he hasn't even. I at least merged the slides. He hasn't even seen. You haven't seen this slide since 2017.
Yeah, right. I do know the gist of it, though.
Well, it's not even like you made the slide. I made the slide in 2017.
So on the horizontal axis is complexity. So at the least complex, we would have just a simple two-way slab, no features. The least complex system, but the highest tonnage. So these are colored. There we are. Okay. So the horizontal axis at the bottom is complexity. The vertical axis is cost. Sorry, no, the vertical axis is cost, unit cost, or quantity. The least complex has the least unit cost, the lowest cost per ton. That's the yellow curve. The more complex it is, the higher the cost per ton on the yellow curve. That's fairly intuitive. In terms of quantity of material, the least complex system generally has the highest quantity of material. So when we're looking at a concrete building, for example, a flat featureless plate will have the highest volume of concrete relative to the other systems, and a waffle slab will have probably the least, even though it's the most complex. So your quantity is going down. Your cost is, of course, the product of the two. And when you multiply them, you see that you get a trough that's down near the lower end. I mean, at least based on these inputs, the trough is down near the lower end of the complexity curve, but it's not at the extreme low end. There is a balance that is not necessarily the least complex. it's something greater than that. The other thing that Shannon started to allude to, but I want to elaborate on, is that a steel fabricator will quite rightly, or a wood fabricator will quite rightly tell you that cost is tied to complexity. They want you to do things that are simple. They want you to do things that are repetitive. Simplifying drives up your quantity, and for sure that affects their cost. But they price things on the basis of quantity, and they know their competitors are going to price them on the basis of quantity. So the owner doesn't pay for the complexity, the contractor pays for the complexity, the owner pays for the volume. And so the lowest price for the owner is not necessarily reflected by the lowest cost for the contractor. Which is why, as Shannon was talking about on Gold Ring, even though the steel fabricator was saying make it less complex, the general contractor was saying reduce the tonnage. Because the general contractor, the owner, was paying for tonnage, and the fabricator was paying for complexity.
The interesting thing there, though, was that it wasn't a GC, it was a design build, but they were used to being a GC, and I was trying to drive home the point to them that they wanted it to be more complex. It was going to be cheaper for them to be more complex, and in the end, there was a lot going on, and they insisted on reducing tonnage. When it finally went to the fabricators, a fantastic fabricator, they were like, this would be a lot cheaper if you added tonnage and made it more complex over here. And in the end, that's what we did. I got the joy of designing it 3 times, essentially, but in the end, that is how it ended up happening. And
we can share that with Walters.
Yeah, Walters too.
We're happy to,
freaking amazing.
Happy to sing their praises.
Yeah, again and again and again.
So the next thing that this is a philosophical point that we want to make is where does the strength of the system come from? We are very used to thinking strong materials are strong systems. So no doubt, strength comes from material. We're very used to thinking that big beams are strong beams. No doubt. So that's the section that you choose. A bigger beam is going to be a stronger beam. But there is a third circle in our Venn diagram here, and that's form, that we can derive strength from form. So double curvature, for example, will create a shell, and that shell form can add strength to our system as well.
So folly is when you have a hammer, everything looks like a nail. So when we first started kind of talking about reciprocal frames, you found that book somewhere. I don't. Did you go out and buy it? I can't even remember. Or did you find it?
The one that was
on the reciprocal
frame. I bought it on Amazon.
But and so we thought reciprocal frames were really cool. We started looking for places to do reciprocal frames. At the time, it might have been folly. We weren't just trying to make people do reciprocal frames, but we had a really cool solution with no problem to solve.
And the only things we'd ever seen were lamella structures, like these long span lamella arches, and then the academic work that had been done at Dow and Virginia.
So we're going to show you what might be some that are folly, but we then slowly found that there was real, genuine applications for these. So what started out as folly for us turned into kind of developing this lecture and this thought process.
So here's a project where reciprocal frame was chosen formally, meaning folly. That this was purely about the form, about the idea of expressing a structural idea in this circular frame.
What might not be clear is that this post is in here. These posts are here for erection. These 2 posts, once everything is installed and connected together, these 2 posts would be removed. Or at least it would be stable if they were removed. They might not remove them, but it could be.
So the next next reason we might do a reciprocal frame is span, and the question is how do you use a 5-meter joist to span 6 meters? Go ahead.
Yeah, go ahead.
So this came from, as it conceptually came from a project where we had an owner that had a very large, I mean it was an open web steel joist system, but it's equally applicable. Had a very large.
They don't care that they're not.
Oh yeah, that's right. They're not talking about wood.
We had to rework all of our ideas to make sure they showed for wood applications.
Yeah.
So they wanted 6 meters with 5-meter elements, but this particular example was 9-meter open web steel joists that they wanted to span 12 meters.
That's right. So this owner had a very large building with 9x9 bays, and was demolishing the building, and was building a new, smaller building that needed 9x12 bays or something like that, and was ideologically attached to the idea of reusing as much of the existing building as possible. That's right. We totally support that idea. So we came up with a scheme that looked like this, where he could use his 9-meter long joists in a 12-meter long span. He needed to use twice as many per area, but it didn't matter. He had twice as many. He was demolishing a larger building and building a smaller building, and so we suggested this reciprocal frame idea to allow him to use his 9-meter joists on a 12-meter span.
You can see just the plan layout of that here.
So another reason that you would use a reciprocal frame is to generate two-way action. Apologize for the graphics here, but this is a Tudor manor with an octagonal tower in the corner, and the purpose of the reciprocal frame here, I think it shows up as the purpose of the reciprocal frame in this case is that it allows them to bring the loads equally to the 4 corners of the tower. Sorry, the 8. Yeah. These are 2 superimposed four-sided frames, this would have had ideological and structural underpinning. That it's a formal idea that the tower is equal on 4 sides, but it also, you're loading masonry, and if you apply all your loads on 2 sides, then things get heavier.
The alternative would have been individual elements that spanned like this. So, these 2 elements would have been hit the hardest. Also, it's also using shorter members this way. You can see that you would have needed long members spanning in that direction to kind of get across that. Or I guess maybe not over the opening, but well, that's also another thing. Spanning, trying to frame an opening with no supports around it. Another good reason to do this, which you show in case study 4.
So the next reason that you might use a reciprocal frame is for complexity. Very often, people talk about lamella structures, and the lamella structure is we'll show you lamella structures, but you may already be able to picture a lamella structure. It's often a shallow arch, densely framed with short members. Lamella, in the formal sense, is a thin scaled plate or layer of bone or tissue, and there's some microscopic views of bone that kind of give you a sense of what the term lamella is getting at when applied to reciprocal frames. So here's some examples of geometric complexity as applied to reciprocal frames. So the reciprocal frame sphere on the left, this is a triangle hexagon reciprocal frame. And then there's a grasshopper. I'm sure there's many, but there's a grasshopper script that's been written that can take any triangulated grid shell and blow up the joints to turn it into a reciprocal frame geometry.
So it's all of these short length elements that allow us to kind of give this illusion of curvature.
I'm gonna break just a bit right here, because you may be looking at that and saying the image in the middle is a grid shell. We know grid shells are good. Why are we talking about reciprocal frames? Why not just do the grid shell? The reason that the reciprocal frame may be better than the grid shell is that for any unbalanced load case, you need an alternate load path. So the shell is idealized for uniform downward load, or whatever load case it's idealized for, but it's idealized for one load case. And any other load case needs another load path. Typically what happens is the load path is bending. So we have shell action, that's the funicular form, is the shell action. Everything is axial, everything is super efficient. Unbalanced loads get resisted by bending. So you get this curved thing that is a shell under uniform load and a beam under non-uniform load. Which means that every one of those little joints is a moment connection. It's a six-way moment connection. So blowing up those joints, making them into reciprocal frames, now there's more joints, but now they're all just shear connections, which certainly makes a big difference if we're talking about wood. Reciprocal frames are not new. The earliest recorded reciprocal frame comes from the year 1270 in the journals of Villard de Honnecourt, who was a 13th century polymath, so engineer, architect, artisan, and he included this in his journals, this little diagram with a quote, "How to work with a tower or with a house using timbers that are too short." So the first use of a reciprocal frame was a purely pragmatic solution to it.
Or the first recorded one that we know of. It was probably done long before that.
Yeah. Well, in fact, actually, I was. What did I see? There was a door looking at indigenous housing, and there was a door or a screen
that
was
sure. I could imagine that.
Woven willow. And as soon as you do a weave, you are building a reciprocal frame. We've got to get that into this lecture, that image. Leonardo da Vinci in the 15th century also included images of reciprocal frames in his Codex Atlanticus. So you can see an orthogonal reciprocal frame on the left and a triangular hexagonal reciprocal frame on the right, which is this one. So you can see the triangles and hexagons built up. Sebastian Serlio was the Italian architect who wrote the 7 books on architecture and helped to define the 5 orders of architecture. And he was using reciprocal frames in built work, and to the point that they referred to them as Serlio frames or Serlio floors for some period of time. So this is a simple orthogonal reciprocal frame. Yeah, no, that's good. John Wallis in the 17th century was an English mathematician, and of course, as you know, he's the mathematician that gave us the symbol for infinity. John Wallis did a reciprocal frame very similar to the Serlio frame. He did an 8x8 instead of a 5x5, and John Wallis did the first analytical solution of a reciprocal frame, solving 25 simultaneous equations. This is for the nerds in the class. I know you all are. For the nerds in the class, he essentially inverted a matrix by hand, which is the way that finite element analysis does it right now, except using computers.
And just, I gave you guys 3 equations to solve. Most of them didn't need to be simultaneously solved. You had solutions for one right off the bat most of the time, and at most you had to combine 2 equations to get your 2 unknowns. But he was working with 25 equations and 25 unknowns, which is just reams and reams of work. I think the most I've done is 6.
Yeah, I can't imagine.
And it was like, and that was in school, like not for fun.
No, high school, because you're a nerd.
A little bit. Wallace he had more than just the kind of standard reciprocal frame that we're looking at. He looked at all kinds of different forms, kind of building on Da Vinci's work and expanding on it.
Armand Rosemi in 1841 wrote the treatise on carpentry, And he included a reciprocal frame in this kind of definitive work as well. This image right here, which looks very, very much like Vallada Honeycourt's original reciprocal frame.
And then even the infill, I like that even the infill within it is also a miniature reciprocal frame. Now it's getting good.
Friedrich Zollinger, 1888-1945, German architect and engineer, responding to a desperate shortage of housing after the First World War, developed what evolved into what the current lamella structures. So this was the Zollinger roof. It was Zollingers were typically Gothic arches, or what they call pointed saddlebacks, for whatever reason. And the idea was that it allowed them to achieve longish spans with short members and a high level of redundancy. Hugo Herring was Zollinger's contemporary, or a little bit after, I suppose. And Herring adapted the Zollinger roof to long span structures for hangars and drill halls and things. So this is and this is what came to be known as the lamella structure. This one in Didcot. And then the Fort York Armory, built in 1935. Did we have to say who the architect is?
No, not in this slide, because I pulled this from the other one.
I've forgotten the name of the architecture firm, but I looked them up, and I followed their history from Marani and something or other in 1930s, and they are RDH today, who are very good pals and wonderfully talented architects. So it was very exciting that to see this in their history.
So this is the armory at Fort York. The only way, unless you feel like joining the military while doing your architecture degree, the only way you can see this building is by kind of lurking outside and looking up through this glorious window. But you can, through that, see the roof. We've tried for ages. We want to get a tour. We want to get in there and see it. Because it's just a gorgeous, gorgeous roof. So, is there value? I mean, all of these things are great. You can kind of see the applications of it, but people always want proof. People want to see a worked out example or something that shows that this can even possibly be cheaper, or if not cheaper, makes value in one.
Value, right?
Adds value in one of the kind of criteria that you would set forth. And remember, I always say that the engineer is helping the architect solve their problems, and the architect is helping the owner solve their problems. The value is in whatever your problem definition is. So your problem might be you need shallow roof profiles. Your problem might be you need lower cost. Your problem might be you need small members, like short members. So it depends on what your value set is, if there is value in this. Is there always going to be value in a reciprocal frame? No. That's why not every single project in the world is a reciprocal frame. It's about finding the applications where they are of value, or recognizing a problem that a reciprocal frame can add value.
That's right. I was going to say, have it in your toolkit for when you need it.
Yeah. So Dave and I set out to kind of take a few projects where we had actually done reciprocal frames, and one where we didn't, to see if we could find value, depending on what your criteria is. Sometimes maybe more than one criteria. So this was a top secret art gallery in Toronto, where we can no longer even remember who the client was because it never got built.
And we were never allowed to say who the client was. We were never allowed to speak the name out loud, so now we forgot.
Yeah, we forgot. Or else we'd be happy to tell you. We're not good at secrets. They had two very, very specific criteria. It's Dave's birthday today, so he's going to be getting happy birthday.
Thank you.
He's going to be getting texts all day wishing him happy birthday, or maybe just that one.
Yeah, that's likely.
So this project had very specific value sets, not necessarily the norm. Normally, cost is all after you meet your other criteria. So before cost, we had the requirement that we needed shallow depth, we had long spans that we had to achieve, and then the owner had another very specific criteria, and that was vibration. Normally for buildings or floors, vibration might be a concern, but it's not usually the governing concern. We check it, but normally we're really worried about vibration for, feature stairs, the things we've talked about so far in this course. But this was one where the owner was highly aware of vibration. I don't know what art they were putting in there, but they were very, very worried about vibration.
It was just long spans, open rooms, public use.
You're killing my story, dude. Shallow depth, long spans, already built in. The owner was cognizant of vibration, which is actually an unusual thing for an owner to actually be bringing up vibration. Getting everyone's back up isn't the right word. Do you remember how we said that vibration is all about perception? So if you have an owner who is aware of vibration, they are always going to find vibration a problem.
They're sensitized to the problem, right?
Exactly. Even if you meet all of the most stringent guidelines, because remember, vibration is about guidelines. If you meet all of the most stringent vibration guidelines, they are going to, and remember, it was about, this is the person that doesn't seem bothered by anything, this is the person that's bothered by everything, and most people are kind of in this point of the curve, and we design vibration for that kind of median range. They're going to, I can't remember what hand I had, but they're going to be the people that are always
not bothered by anything, bothered by everything. That's
exactly.
The scale.
Most people are right in here, so this was a client that was going to be bothered by everything. So we started out looking at regular framing. So we did a framing analysis, did sizing and deflection checks. So this meant we met our National Building Code of Canada strength and our highly recommended deflection guidelines, which are standard pretty much, internationally. 5 members, deepest member was 494 millimeters and a total volume of just over 7 cubic meters of wood. Volume is a good representation of cost if you're talking comparatively. Piece count and depth. So here's your kind of basic framing outline for that. The second system we looked at was a reciprocal frame. So a standard reciprocal frame where that's a member and that's a member. And I show a plan of it right there. So the piece count went up to 10 major members. The deepest member was now shallower. So we had 494 and now we only had 456. So it was shallower. Our volume went up, but if this was going to solve some of the other problems, the client was going to be happy. So an increase in cost was not going against the value set of this project. I mean, finding the cheapest option within all of those criteria was definitely a concern. But it being the more expensive option was not going to be the worst thing in the world.
I just realized, go back to that slide, we say piece count of 10. I wonder if that's why that person thought it was a weave.
We got a weird question after our lecture. I think they just didn't understand.
Yeah, someone looked at the diagram and thought that we were weaving beams, literally.
Literally weaving for all of the reciprocal frames.
Yeah.
They thought that, not just that one. I think because it gives the illusion that they're woven. That's why I said here the major elements, because these ones here were just infill. They were like 2x4s. Yeah. They weren't the big members. So the major members were there was 10 of them. So the question now is, do we take our deflection criteria for granted? I've talked about how it's a guideline, and sometimes we don't even use that guideline if there's a good reason not to. We don't do it lightly. But what about the applications where maybe it's not rigorous enough? And so when would that even be? Well, it helps to understand why we have the L/360 criteria for live load. Now, it's dead plus live is L/240. Same idea here. So if this is the shape of our L/360, which is almost a circle. It's not exactly a circle, but you can imagine it's pretty darn close to an approximation of the tip of a circle. So this is what we're measuring, and we calculate this point right here. So that's our L over 360. But look at the line if we draw it in the opposite direction. We get that first element has a very, very, very steep slope right here. In fact, if we look at that, it's a 1 to 60 ratio. So for every, so it's a very steep slope here. And so let's talk about where L over 360 comes from. If we're talking about a standard beam, and we look at our L over 360, and we approximate this to a circle, which is pretty darn close to it, and we look at this tangential line to our curvature, what we're really saying is we're trying to, so this is where the slope is the steepest, and where the slope is the steepest with an L over 360 criteria, we're limiting that slope to 1 to 90. Our 1 to 60 is a much steeper slope right here. So that criteria for the very first two bays were in excess of this L over 360 if you thought about what it was doing. And the reason that's important, you can imagine, is that that is now where all of your floor finishes are going to crack. You are not meeting the intent or the spirit of the L over 360. Now, people do it all the time, but we had kind of fragile finishes going on this, where the owner was going to be highly aware of any cracking whatsoever. I can't remember, but I'm going to assume it was polished marble imported from some rare
place
mine.
that has polished marble factories.
You just want to do it to me today and just drive me today.
It's your birthday.
Stop. I can't get mad at him. It's your birthday. Okay. So let's go back to the standard framing plan. But let's try to meet this kind of more rigorous deflection criteria. Let's look at that very first framing plan, but meeting this updated deflection criteria, because we know that this owner is going to be watching this spot right here. Even though we would have met all of the due diligence and all of the standard of care that is outlined by the code, if you have a litigious client who you already know wants above and beyond, you probably want to try to find that, and as long as you're clear to them what the thought process is, you can go above and beyond the code. You don't start there, but you can definitely go above and beyond the code. So we said, listen, we think this is where you're going to be unhappy. If we wanted to do if we wanted to do a regular framing system, we would recommend tightening up the deflection criteria on these two bays here to kind of meet that slope to be 1 to 90. And with that, these two end members, the deepest member became a 570 deep. So our piece count stayed the same at 5. Our deepest member is much deeper now, and our total volume goes up. So let's just take a look at those three options. We're going to say that this one does not work because it doesn't meet that 1 to 90 slope on the very first two members. So our reciprocal frame and our standard framing with a heightened deflection criteria. So you can see our piece count goes up, but our total depth is much shallower. And if you remember, that depth was one of the driving values of this project. So yes, the volume goes up, but sometimes understanding that you're meeting other criteria here. If this had been this depth here, they couldn't build the project because they had tight headroom spaces and they were using the framing, so the masonry out shell of the building was an existing building. So they couldn't make the building a little bit taller. They were set by the walls that were already in place. So making it deeper meant it would not be built. So the value of this being slightly more expensive was irrelevant because it was the only way it could be built. So let's talk about one other thing. The owner had a vibration awareness. And one of the good ways to kind of talk representatively about vibration is to apply that 1 kilonewton point load that we've talked about. We know that it is not the measure of vibration in its entirety, but it is a very good quick check to see how behavior plays out. For small scale...
What I tell people in the office is that the deflection under 1 kilonewton point load is indicative of vibration performance. The lower that 1 kilonewton deflection, the better the vibration performance is going to be.
Exactly. And so it works really well on small scale elements. Like you can pretty much count on it. If you can meet that, and if you can meet a 1 kilonewton under 1 millimeter deflection, you're still going to have to do your vibration check, but you'll at least know for preliminary design that you're in the realm of reasonable. You might have to tweak things a little bit when you do your final vibration check, but you know you're in the right spot. It's a little bit different for this scale of structure, but you can use that 1 kilonewton point load to talk comparatively about two systems. If you can compare their relative deflection under that 1 kilonewton point load, you can see which one is going to behave better under a vibration criteria.
That's nice to put.
So if we take both of these two systems and apply a 1 kilonewton point load, it's not going to tell us if vibration is okay or not, but it's at least going to let us see which one behaves better than the other. And you can see under a 1 kilonewton point load, all of the load is being carried by one beam, so even though you have all 5 beams, only one is looking after the vibration at any given time. And we're going to see a 0.6 millimeter deflection. The reciprocal frame forces the engagement of all of the members. And so we end up with a lower deflection. Now, these don't say, does vibration work or not? But it gives us a strong indication that this one is going to behave better under vibration criteria. And if we have a client who's highly aware of vibration, we can see right off the bat that this is going to be a recommended system. While we were giving this talk the other day, Dave kind of had an enlightened moment where for damping, for example, every time you have a connection or a joint, you actually increase your ability to dampen the loads. We don't see any damping until the edge, and you only have, for any given member, 2 connections that you're going to get to use to kind of dynamically help reduce your awareness of your vibration.
The damping is the absorption of energy, I would just remind. So,
yeah.
So when you have a joint that's rotating, you've got friction in the joint. You get bolts slipping within the holes, you get friction against side plates, and it absorbs energy.
Whereas this, applying your 1 kilonewton load here, you have, I should count it, but so many connections now, and each one slightly damping that load or absorbing the energy from that load, which decreases the vibration kind of peripherally out around that point.
Right. As soon as the higher the damping, the quicker the vibration dies out. So you're less annoyed by an impulse, a single impulse, than you are by an impulse that reverberates. Thank you.
He's always correcting how I pronounce things, so that was a fantastic small moment for me. So in the end, we didn't do any of those. We did a hybrid system that basically took advantage of all the things. So this was a very project-specific construction element where we did end up with some moment connections, but the moment connections were shop fabricated. In the end, it never got built, but this is what we were intent on putting on the drawings. What was great is, so you can see we have 5 pieces plus some infill. The deepest member actually is the shallowest of all the options we've talked about, down to 418. And the total volume went down somewhat from the purely reciprocal frame. This gave them some control in the shop, and I'll show you here what the framing system ended up being. They fabricated each one of these elements with basically outrigger arms off of it, and then created shear connections in between here.
We called these tree girders, didn't we?
don't remember.
Yeah, we give everything a name. We know architects like names, so we name things.
From henceforth on, this shall be, I dub thee, tree girder system.
Yeah.
I don't remember you ever. It's either a heat turning on or a kid awake. That is a kid awake.
That's a kid. Oh,
okay.
Have fun talking about tree girders.
I'm just going to go for a few more minutes. We're going to break this into 3 or 4 recording segments. I now have the ability to thread all of these together. So for you, it'll be one continuous lecture. So what was great is they could fabricate these on site. It meant they had stability during erection. This is something we probably haven't mentioned, is that reciprocal frames, a true reciprocal frame where everything is a shear connection and no moment connections with small elements, it's not stable until the entire thing is erected, or at least segments of it, fully spanning segments of it are erected. This gave them stability during installation, so it wouldn't have to shore quite the same way. It gave them two-way action still, so they were able to kind of take the benefits of everything. In the end, it was never built. The project kind of died. It might come back to life someday, but it would have ended up with elements of everything. Now, this had the luxury of being able to do moment connections right here. Again, this was meant for a wood lecture. We were actually looking at something in steel for this project. We have a couple more case studies. So here's the second case study. This one was this one's built. It's in kind of rural PEI, a difficult site to access for large-scale construction equipment. So a crane couldn't get back to this site. You can see that there was existing structure in place, and one of the requirements was that they needed to be able to carry things onto the site from wherever they could park the trucks. The form of it was 2 raised edges and 2 sloped out edges. The classic framing method for that would be a sloped valley beam. So you can see these 2 sides are the raised edges, and then these 2 sides sloped down. And typically we would use a sloped valley beam to create that profile. The standard framing with a valley beam would be 15 pieces, a total volume of 5.8 meters cubed, but the largest element is 731 kilograms. The Canadian labor laws essentially say that a single individual can only lift something that is 66 pounds, or about 30 kilograms. So you can see here that this was going to take a lot of people to be able to kind of walk this from some distance off-site onto the construction site. Getting several people to kind of work in unison to carry one thing is very difficult. All of them working at their maximum kind of lifting capacity, even more difficult. So we wanted to give them options where it might have added complexity and it might have added volume, but it was going to reduce the weight of each individual member. So here, one big member, but lots of light members. So we said, what about a reciprocal frame element, where we have 4 beams that are approximately the same, and we still meet the same framing profile of the roof. Our deepest member went down somewhat. Our piece count goes up quite significantly, but our total volume actually came down. And here's the biggest one. The largest piece was now 268 kilograms. So like 6 people now, not more than that. 9 people now could carry each one of these elements. The one thing we didn't like about this is, you can imagine if that's your ceiling, you've got these elements kind of punching through the ceiling. So we said, we have one more idea. This one was our favorite. So if you put a ruled surface on a hyperbolic paraboloid shape, you can still get a ruled surface to achieve your curved element. So this is still a ruled grid here, you can see, but by taking individual elements that are smaller in length, you can still achieve that double curvature of the roof. So you can still see we still have our straight-edged roof and our sloped lines. Your decking would warp somewhat, but again, it's going to individual members, and we see curved decking all the time. It's the thinnest element of the profile, whereas the thinnest profile, which means it curves quite nicely. You can see that everything is the same depth, nice and shallow. Our piece count went up from option 2 somewhat. Our total volume is actually not bad, but here's the big one. Each element is about 60 kilograms, so 2 people can carry it. We didn't put this image in our Australian lecture the other night, and we thought it was more architects than engineers. It turns out there's quite a few engineers in attendance, and so we really wished we had included this. You can see that the elements with the peak moment are around the perimeter, and you can see that the peak shear is around the perimeter. So here's a summary of the 3 options with kind of images showing their depth. Largest piece, which was a big driving factor for this project. Total volume, the reciprocal joist method, not the highest volume, but it did have the highest piece count. So it really comes down to what is the value set for this project. I think in the end, they just tore up the lawn and did stuff and made this one work. So this is where not understanding that complexity can sometimes add value came out to the detriment of the project. And we think the detriment of the project, maybe not someone else. So this was a 3rd case study that we set out to do. There was a oh, 2 boys. Hi, gentlemen. Do you want to come say hello to all of the students? Can you say hi, all the people?
Hi.
Duncan, are you confused where all the people are?
Hi.
Where are all the people? Blow them kisses. Okay, go eat your bananas. I'll come in just a minute.
Banana monkeys.
So this is a problem that we come across all the time, and we kind of did this as a lark just to see if it could solve a depth problem. So building maybe on a corner lot or a storefront, you see this kind of in downtown Vancouver all the time where they all have continuous canopies, where the building edge is pulled back from the roof line so that you have an overhang or a canopy. Inside, you have mechanical ducts, all kinds of stuff, usually a dropped ceiling, but often at this perimeter element, the architect will say, we want to do whatever we can to shallow up that profile. It doesn't need much, it just needs a soffit, and so we want that to be a nice crisp edge line. So shallow soffit here, big driving factor. We wanted to see if we could take the standard framing plan and improve it by using a reciprocal frame to give us a nice shallow edge here. We got some added bonuses in with that. So this would be the standard framing plan. This would be an element that cantilevers out past this column, picking up this beam. This beam comes to here and cantilevers past this point and picks up this beam. And then this one would be typical of all of these other joists. So this beam and this beam start to be responsible for doing all the work. We probably only have about 2 minutes before they come in wanting something. So this meets our standard deflection criteria, piece count of 9 major members. Most of the members were 494 deep, and the 2 major ones, these cantilever ones, were 570. So that set soffit depth by these 2 members here at 570. So the deepest member was also in the soffit, which now drove the soffit depth. total volume of 12.2 meters cubed. So standard framing plan, there's a section through the soffit. We said, let's do something kooky. Let's make this corner a reciprocal frame. So this beam here is on the diagonal, not moment connected to the column. So it's a teeter-totter on top of the column. It's not moment connected, which means it's not stable until all the framing is in place. But it stops becoming a teeter-totter because for this to tip over, it would have to lift up the other edges. So once everything is in place, it becomes stable. I always joke that if it's not a right angle, it's a wrong angle, and that's kind of how I live my organizational life. Sometimes you have to, I'm a bit OCD, so that's why Dave is making that face.
You also sound like your father.
So this element being on a diagonal is kind of breaking the norm. And most engineers tend to think in a very linear manner. So this here, this cantilever's at both ends, but it doesn't have the big long backspan. This element here, which was one of our, big framing elements, now isn't too bad. We have this element here doing lots of work, which is a simple framing span. This doesn't have a long backspan because it's getting picked up. No, it's just spanning from here to here. And this one's spanning from here to here and picking up that one. So we have lost this big element that was doing all of the big hard work because it's just spanning from here to here now. You can see it better in this framing plan right here. So this element, which is picking up all of these joists, is still a 570, but it is now within the kind of interior zone depth. You can see it here. This is a cross section through the soffit, and nothing in the soffit now is deeper than 265. So at the soffit before, we were at our 570 limit, and now we've dropped it down to 265. Here's where the bonus kind of piece for us was the total volume is actually greatly reduced. We did this to prove that we could show that the soffit depth came down, and it was a delighted result when we found out that it also had a reduced volume count for that system. So here the two are in comparison. You can see the standard framing and the reciprocal framing plan. The piece count goes up, total volume goes down, and the soffit depth goes way down, and that was the driving case here. The interior depth actually doesn't change. There was a 570 somewhere back here in this framing plan too.
So here's the highly pragmatic solution. This is where if we set out with reciprocal frame as the idea, we can find projects to apply it. If we have a reciprocal frame in our toolbox, then it becomes a solution to certain problems. This is a house for an art collector, big open plan. This is the upper floor. We're looking for a way to frame the roof. It looks really conventional. We have perimeter load-bearing walls. We have a nice line of support right down the middle. Right down here, we could put a beam, span joist this way. Very simple, we thought. But let's have a look at what's happening here. We've got a little section of sloped roof on the outside. And the sloped roof is effectively an opening. We can't take a beam across a sloped roof. No problem, we can bridge around a typical opening. We have strategies for that. Until we look and realize that we have another opening right there, which interrupts our trimmer elements for the sloped roof openings.
So what we would have done is we would have had a major beam here, and we would have framed that opening right here, like that. But we can't because we've got that sloped roof there now.
That's right, and this element that would have been the trimmer for that opening, that trimmer would have been up to here, and it's interrupted by this one. So we have two trimmers for two different openings interrupted by each other. Our solution is very simple reciprocal frame.
no one will ever see this. It's going to be hidden behind a drywall ceiling. But it became a very pragmatic solution to a problem that we face all the time.
That's right. In fact, I mean, many architects, Renee McKay-Lyons is fond of talking about her father's pinwheels, that inevitably there will be an opening and an opening, and the right edge of one opening needs to align with the left edge of the other opening, so that you cannot run a piece of structure through. And the reciprocal frame is a solution to the pinwheel problem. This is
so I put this back in. You haven't seen
yeah.
these slides in a couple years, so I just wanted to remind you that he hasn't. This was a case study that he's talked about at OAA lectures and RAIC lectures, but you haven't seen these slides in a couple years, since we had kids, I think.
So this is an inflatable structure. It was a competition that was won by Canva in Montreal. They were needing to replace the infrastructure below St. Catherine Street. And St. Catherine Street, you may know, is a major economic engine in Montreal. It's the major retail street. It's a little bit like Yonge Street might have been in the 80s or something. And so the disruption of upgrading the infrastructure below St. Catherine Street was going to be a huge economic problem in Montreal.
And it had happened on the sister street.
That's right, on Saint Laurent.
On Saint Laurent, like 3 years previously, and basically 60% of the businesses on the street closed during that. Even though they were open, people didn't know. They just thought it was a construction site and just stayed the heck away.
So the idea behind it was to create construction hoarding that was festive and created a carnival kind of atmosphere and brought design down to a construction site. Our solution to this was a reciprocal frame. So what we need to do with an inflatable structure is, it's intuitive. When we're inflating sausages, we need to connect them all together in some fashion. Here's our analysis, our general analysis. And then we came to look at where they all met together in the corners. This is how we start tying it in.
The plan didn't start with reciprocal frames.
No,
the plan started with a series of tubes stitched together that would all inflate together at the same time.
Thank you. So we did a little detailed study of a corner, and found that a right angle corner works reasonably well. It swells up a little bit like an aneurysm because the elements don't go through, but it works reasonably well. And this would be a conventional solution to this problem in a fabric structure. Where we have elements that are meeting at very acute angles, it behaves quite differently. So it doesn't retain its geometry. And Shannon gives me a hard time for the hammer pants, but really this is what it winds up looking like.
Mostly because like these deep crotched pants were really uncool when you made this slide. They're actually almost popular.
Well, then it's not funny anymore. Then. I'm gonna have to find a new reference. So with the very acute angle, they tended to swell up, and they lost the geometry. It kind of lost the architectural intent. Also, we ended up with very high stresses. So what we did then is we said, what happens if we run one through? Is that obvious?
No.
It's really not. So it's maybe just a little more obvious here. Anyway, the idea was, let's look at running one of the tubes through and breaking the other one and connecting into it.
I won't draw it. You're already past it.
Now the fact that the one tube runs
It's
through.
slightly more obvious here.
Yeah.
You can see that You
Yeah.
can see that this is a tube, and then it's two separate tubes kind of coming
Yeah.
to the side of it.
So doing this now preserves the geometry and also winds up with lower stresses through the joint. The idea of making it a reciprocal frame.
Good job, buddy. I'll come get it in a minute.
Oh, here we are. This one makes it very clear that it's a reciprocal frame.
Yeah.
So what we did is, looking at one of them, we still need to inflate the tubes.
Yeah, that's the
And-
problem.
and so
And you don't want 10 pumps.
Yeah. So we need air balance. So this is a reciprocal frame with a hole in the tube. And for air balance, we did a detailed study, found that it did preserve the geometry. And here then is our final assembly. This is where this was all coming to. So in order to preserve the geometry of the joint, we found that taking one tube through and breaking the other one would give us a satisfactory joint, and then manufacturing it as an inflatable reciprocal frame wound up being the effective solution.
Who knew bouncy castles were so complicated?
Yeah, it's funny to use bouncy castle colors in this as well. We sell this at Costco tomorrow. Okay, so let's look at some examples.
And some of this is just going to be anecdotal stories, things we know, things we don't, because some of these are images that we're back engineering because they're not ours. This one's actually interesting. We gave a version of this talk last year in Helsinki at the Nordic Wood Form lecture, and we were on the second day, I think, of lectures, and we gave our reciprocal frame talk, and we showed this image, and we talked about this architecture firm, because that's who's listed. The show stopped. We have no qualms about just pumping them full of YouTube videos at this time of the morning. So we talked about, we showed the image, and we really like this image because it is similar to a project we did in 2007, and we like that other people kind of grasp this concept and use this concept. At the end of the talk, somebody put up their hand and they said they loved the talk and they wanted to talk about this because they had some information on it, because they were actually the person that designed it. And it was Tony, who not only had designed it, but was actually giving the talk right after us. So we don't know if we were his opening act or if he was our follow-up band. We don't know. We're just gonna roll with it. He was able to kind of give us some insight on that, which, I mean, was exactly what we thought it was, but we just thought it was an interesting story that we were giving a talk on reciprocal frames, and one of the people who had designed one of the reciprocal frames in our lecture was in there.
So they must be the world masters of reciprocal frame geometry, because if you look up in Wikipedia, if you look up Frederick Zollinger, there's a series of footnote references of projects in the world today that use the Zollinger system, and 2 out of 3 of the reference projects are geometria projects. So I feel like I should go in and update the Wikipedia page with some of our projects.
For sure.
This is the Discovery Center in Ventura, California. This is a 1940s lamella that would have been built originally for an industrial purpose. I think it was an aircraft hangar, perhaps. That's been since repurposed into a family entertainment center. So what we're looking at here is bowling lanes, and you can imagine what a glorious space this would be for a birthday party, which appears to be what's happening
I'd bowl
in that image.
Not anymore.
That's right.
So this is the Canadian Pavilion at the Venice Biennale. This was brought to Blackwell not to do the original structure, because this had been well established. This was one of the artists, this was John McMinn, who was doing the 2008 Canadian installation for the Venice Biennale. And they knew that they were going to have to hang art elements from inside this building. The problem was, as much as there were drawings of it, it wasn't clear what the exact dimensions were. Everyone knew approximately what it was, but these supports needed to connect perfectly. So we needed a support structure that could be fabricated in Canada, shipped over to Italy, and then installed by the team on site that allowed for deviations from the anticipated spacing. So we were pretty darn close, but not to the within 5 millimeters that we might have needed to install this. So when Dave started looking at the structural drawings, he was delighted to see this form. You can see that we have all of the markings of a reciprocal frame, and our guess is that the intent was for these dashed lines, so this to be here and this beam to continue right to here. Instead, this beam is missing and there's a column right there, which is heartbreaking because this could have been a truly glorious reciprocal frame with no column right there. We were guessing, and that was the architect's intent, and somebody at some point said, no, you can't do that. Whether it was the engineer or the building department, the local building department, somebody said, no, you cannot do this. What was really cool is that in doing this, Dave developed a reciprocal frame system that could be installed between these beams that allowed for tolerance and installation. So you can imagine all of these elements could be prefabricated, and if we allowed those joints to slide relative to each other until they needed to be locked in place, and I'm assuming you did a hand tightening, like a Halfin channel system of some sort, that you could, like a lock bolt that you slip in and...
Yeah, it was Unistrat, and I think all we needed to do was rotate the joint as opposed to even sliding it.
Yeah. And by doing that, you can imagine that if this was over here just a few millimeters, you could tighten up that parallelogram right here and get this whole system to span that tiny little bit farther. So there was a lot of play built into the system.
So here, reciprocal framing was used for tolerance. Again, it was an entirely pragmatic choice, not a formal one.
He's loose.
Yeah. So this is Seiwa Exhibition Hall by Kazuhiro Ishii. Ishii has done a lot of reciprocal frame work, and the Japanese architect. This one has two things going on here. One is there is a conventional circular reciprocal frame in the top with an oculus, if you can call anything to do with reciprocal framing conventional. But then there's also this this lovely star form down below. Again, you know, it is a circular reciprocal frame just with a very large oculus relative to the outside radius. Also Ishii, this is the Banraku Theater, an orthogonal reciprocal frame, also in heavy timber. Here's some reciprocal frame elements that are used for sculpture. Rhinus roll-offs, a reciprocal frame sphere. Unfortunately, we don't have an image of it, but Shannon did something very similar for Nuit Blanche 2 years ago, which we really need to get an image of in here. So a reciprocal frame sphere. You can see the hexagons and triangles. This is the same system that Da Vinci developed 500 years later. Also, Rhinus roll-offs. This is a landform sculpture, an orthogonal reciprocal frame that just kind of floats above the forest floor. This is the one that started it all for us. The Hill County Animal Shelter by Rural Studio.
Which we didn't do.
We didn't do. But this is the one. This extremely beautiful project is the one the first contemporary reciprocal frame that we became aware of that inspired some of the things that we did. And sort of a sister project, I mean, also an academic project, this is the Ross Creek Picnic Pavilion that Ted Kavanaugh did with Coastal Studio associated with the Dow Architecture School. So this is a beautiful picnic pavilion. One thing that I find interesting that is going to become relevant a little bit in a later project, if you take, if you look in plan at a reciprocal frame lamella structure and you follow the diagonal grid, one might expect that it winds up chopped off on an angular plane. But in fact, when you follow the diagonal, you trace a helix. And so you can see that very plainly in this, in that one image that Shen's tracing right now. Serpentine Gallery Pavilion in 2005, Alvaro Cezanne, Edward Soto de Mora, and the reciprocal frame, it becomes very apparent from the inside. It looks much more just like scales on the outside, but on the inside you can see that very much a reciprocal frame. Gore Meadows. This is a contemporary lamella structure by ZASA architects. Bright Design were the engineers and fabricators, I think. But this covers an outdoor skating rink in Brampton.
What I like about this image is that it shows it in construction. You can see that they had to complete a few series of the arches for it to be stable. As I said, you know, it's not stable until it can fully kind of complete the arch or whatever kind of support to support we're talking about. And they would have to shore in between or give some sort of connect. There's always a little bit of inherent moment capacity in any connection. It's about not exceeding it. And in fact, it looks like what they did on a few of these connections is actually put in moment connections that we are inferring were about, oh look, could I be writing in my lectures again? I might be able to be writing on my screens. So we might have been able to, you can see that we're inferring that they might have done moment connections here just to help them be able to install this system. You can see it here kind of completing its arch. We've talked about arch systems having thrust. You can see here that this looks very similar to what you see at the ends of bridges. There is an outward thrusting force here that needs to be resolved, and they actually sculpted the foundation piece to reflect that. And then here's a close-up image of it with the roofing on, and you can see the individual members. Gorgeous. You can see just a hint of the connections here, but they've done it in a very crisp, clean way.
This is a UBC transit shelter with fastenat. Now, when we look at this, it is not apparent that it is a reciprocal frame in any way. But when we look at the actual fabrication details, we realize that in order to minimize site work and minimize piece count, they manufactured these in multi-segment pieces that then were connected together in the field. And then the way they were connected together in the field wound up resembling a reciprocal frame. So the behavior, even though the form is not reciprocal frame, the behavior winds up being reciprocal frame.
So this is one that I was the engineer for 2005, 2006. At the time, there's a few interesting things on this project. At the time, what you wanted to do was a reciprocal frame. The architect wanted it to evoke an upside-down canoe. Dave really wanted to make it a reciprocal frame.
As did the architect, actually.
Did they? Yeah. And was it the contractor that was just so? I was a relatively not junior, but I was not far off of junior engineer at the time, so I wasn't a part of all the meetings. I just did the grunt work.
Yeah.
What ultimately happened there? Did they? It was just too complex for them to get their head around.
It was complexity and erection complexity.
Yeah.
So the feedback from the fabricators was that they needed to erect girders so that they could stand something in the air and then suspend framing in between.
So instead of having kind of a uniform system, all the same depth, we ended up with major girder lines here with infill elements, and then they saying the show stopped about even smaller infill elements here. It was also in this project that Dave was at a meeting, and Nor had one of the, because Nor has an engineering department, and one of the kind of it was a co-op student. He was a co-op student at the time.
12 years old at the time.
Say that you're just doing it to me all day today. Yeah, buddy.
The show stopped.
No, it didn't. That's a joke. Everything's frazzling me this morning. Sorry. Okay. Dave was at one of the meetings where a co-op student who was with the NOR engineering team was sitting there, and Dave was saying, what we really need here is castings. We could create exactly what we wanted here. At the time, that co-op student was doing his master's in casting research for structural applications, and for him, a light went off that, oh, there are architectural implications for this as well. So if I'm going to start a company eventually for structural castings, I can also incorporate architectural features as well. So that's Cast Connects, who I ended up working with for 2 or 3 years, and they're the ones that did the giant cast nodes at 134 Peter, which is where Dave's office is now. Those guys are way more successful than us, making way more money, and internationally known, and working on some of the coolest projects in the world.
Absolutely, yeah.
So hats off, Mike and Carlos. The fun, awesome team there too.
And it all started here.
Yeah, Dave's going to take personal credit.
Yeah.
Actually, Carlos loves to tell that story as well. Whenever we see him out, he always tells that story.
Now, I have to say on this that this was not the intent, but in the end, the architect kind of fell in love with the Argyle appearance of this roof, the kind of hierarchy of large to small elements. So it was nice anyway. Okay, this is one of my absolute favorite projects, favorite reciprocal frame. This, of course, is the glass cube at the Apple Store in New York, or the former one. They've since replaced it because this one was too complex and the pieces of glass weren't big enough.
Because at the time, structural glass was not. I mean, it's still barely done, but it was brand new. Like, it was groundbreaking in so many ways.
So the driver for this project was that it needed to be a cube. All sides of the cube are the same, and so there was this intent that all 4 walls would be bearing the load equally, and they could all be the same. Which meant that you needed a two-way system for the roof, and you've got to have a two-way system. I mean, beams are inherently a one-way element, a one-way structural element, one-way system.
Which we saw in case study 1. The main framing system was just spanning from wall to wall.
So the kind of brilliant innovation, and again, an entirely pragmatic solution to the problem, is you make the roof out of a reciprocal frame, which brings the load equally to the 4 sides. This one was folly. This is a guy in West Toronto that was building a garage, and he had some money, and he had a sports car that he wanted to show off, and he came to us, possibly having seen a project we had done before, possibly just out of on his own, but he came to us and wanted to do his garage as a reciprocal frame. And
So this is where folly, though, can have value. For him, the aesthetics of it wasn't folly. The aesthetics of it was the value.
Right.
So we say folly, we should be careful, because folly doesn't mean bad.
Folly means formal. Like
Yeah,
it was,
yeah.
the decision was based on the form specifically, and not
Yeah.
falling out of pragmatic concern. This would, so just a week ago, I get a press release in my email from a guy named Steve Webb in the UK has just won the IABSE Gold Medal, which is the International Association of Building and Structural Engineers. He's an extraordinary engineer, well deserving of the gold medal, and this was the image that was in his press release. He's built a house. I suspect that this is a house he built for himself, but I couldn't find that to verify. But this is a structure that was built entirely to show off reciprocal frames.
And you can see the roof is reciprocal frames as well, as much as we haven't highlighted it, as is the perimeter bearing walls, which would also be acting as a lateral system.
Yep. This is the Toscana thermal baths in Bad Orb, Germany. In this particular case, a reciprocal frame was chosen to achieve the geometric complexity. So it's a grid shell, and I mentioned that a grid shell is a 3D funicular form that is idealized to a single load case. Other load cases need different load paths. Often bending is the alternative. And the way you achieve bending stiffness, two-way bending stiffness in a system that's built up out of framing elements without moment connections is a reciprocal frame. And so that's exactly what they did. The precedents you'll see for big grid shells like this are bending active. So typically the elements are continuous and they're sprung into place. Like the Mannheim multi-hull is a bending active grid shell. But those are extremely complicated to erect, and they involve a lot more construction risk. This is really straightforward. It's statically determinate, and the geometry is controlled in fabrication. This is the competition-winning entry by KPMB for the Jack Layton Ferry Terminal, and we were involved helping them with this. Hopefully it'll become a built project one day. So this is the exterior, so it's a compound curved form with landscaping on top of it. And this was the image from underneath. Our proposition for this was a reciprocal frame, so the reciprocal frame gives us two-way bending stiffness and also facilitates the complex geometry. But the reciprocal frame was unlikely that it was going to be able to carry landscape loads. Our proposition was then also wood is not ideal for carrying landscape either, because it's if there are leaks, it's vulnerable and it's vulnerable to damage as you're installing the landscaping. So our proposition was to take a reciprocal frame and make it composite with a concrete slab, which we would then void with bubbles, with the bubble deck bubble system.
That might make us rich one day.
Yeah.
But I don't think so.
Yeah, good luck.
Because Dave tells everybody about this.
That's right, yeah. It's going to make
Get your patent in now. Beat us to
somebody
it.
rich one day. Carlos. This is a curtain heliport. This is a project we did where the architect came to us, said this is for a building owner, a wealthy guy who owns a helicopter and loves his helicopter and commutes from his house in Collingwood to his office in Toronto every few days in his helicopter. So he needs a hangar for his helicopter. And the program, it was a triangular building, and we started talking about structural solutions. But the thing about a triangular building is it sets up a hierarchy. It respects one wall, or conventional framing in a triangular building. It respects one wall and ignores the other two. So we wanted to come up with a framing system that was more democratic to the three walls, and the solution that we proposed was a reciprocal frame. It's not a three-way reciprocal frame. We could have done that, but it was and then the final resolution. The final resolution of it was extraordinary. We used, these are nap concealed connectors. These are nap concealed connectors so that everything is completely concealed. It turned out to be extremely beautiful.
We're almost, I don't need to talk to you guys in baby talk. We're almost done.
One of the last ones, or maybe the last one we're going to show you, second last one we're going to show you. This is a bridge that Bob Davies designed for his own property. Why don't you tell this one?
We were out for dinner with Bob Davies, who's a partner at Montgomery Sizem, and his wife Anne McElroy, Brooke McElroy. They were talking about their property that has a creek on it. And we had just seen the viral video go around of people building Da Vinci's bridge kind of in their backyard just for a lark. And we showed Bob and Anne. About 2 months later, we got photos from Bob where him and his sons had made it their summer project to build a two-segment version of the Da Vinci Bridge, because that's all they needed. But you can see here, maybe you've even seen some of the viral videos of it. If anybody wants to change their element that they're building, hats off to you. I have no problem with a change. It's never too late for a good idea. If you want to revise what your structure is going to be for your model.
But you should know, actually, that there's a student group at the McEwen School of Laurentian that is doing a structure like this. Daniel Moses is helping them out.
I was thinking their possibilistic version. I'm talking about their scale model that they're doing for our project. He has no idea about the project whatsoever. There's a project?
Am I supposed to do it?
I've already done it for us. Yes. So you can see here, they went and did a two-frame version of it. So it's not stable until it's all together, but it's just perfect. It just sits on the ground. There's no foundations. It doesn't cause any erosion for the banks. So it kind of met all of their criteria, but they can now walk throughout their property. And then this is a project Dave and I did in 2009 inside the Native Child and Family Services headquarters at 30 College. The project had been long and complicated, but wonderful, because the architects were great, the owners were great, and the contractors were great. That was Bosco and Verity did the contracting for that. So the whole process was delightful. But it had been going on for a long time. It had been like 2.5 years of kind of relentless work. Levitt Goodman Architects came to us and said, we want to talk about a kind of a modern representation of a longhouse. We have some ideas. Here are just some kind of drawings of kind of textures and fabrics, but we want you guys to kind of do something innovative for the interiors. And we're like, okay, and they left. That was the end of the meeting. And Dave and I like, we almost sat until they left, and they were like, yes, reciprocal frame, reciprocal frame.
The Hill County Animal Shelter had just been published like within 6 months of that.
Yeah,
so it was on our minds.
It was very much on our minds, and you can sell it for sure, buddy. So we ended up doing some structural analysis. Now, this had the bonus of being an interior structure, so we only had to worry about kind of interior pressures, one person climbing on it, or maybe for maintenance. But otherwise, the loading required, so no snow, no wind, the loading requirements on it were low. But we did know that it needed a manual labor force of volunteers. So when I say unskilled, I just mean that it's a bunch of volunteers coming in to help build this. So we did the structural analysis, found a system that worked really well, and Dave did some innovative things that he'll talk about on the next slide. But we ended up creating 3D CAD, and this was in late 2007, early 2008, and sent it to the architect and said, what do you think of this? And they said, we love it. We've sent it to the builders, which were MCM 2001. They've already started fabrication. So there was no contract documents except for a 3D CAD file, which at the time was edgy.
Yeah, it doesn't seem like it now, does it? Rhino didn't exist yet.
Yeah, there was all of the 3D modeling software that we're just so used to now didn't exist. The other bonus lecture I'm going to give you guys and record later is about complex geometry and representation of that complex geometry. How do we create contract documents and tell people how to build complex things? But what was really cool about this is how Dave solved if you guys remember, he talked about...
Daddy, hold my foot.
Hold my foot, Daddy.
Okay.
Okay, you little kook. That if you tried to cut off the end of this, it would follow a helix. It's not just a straight line in plan. It's actually this kind of curved helix. And then, so how do you take that line and then wrap it around the round edge of the longhouse? So you can see it here in plan. And here are the lines of reciprocal frames that Dave laid out.
So what we did is we were puzzling how to come up with a.
You can see the helix really nicely here. Like had it, I don't have one drawn on the straight line, but you can see it here. You can see one of them here. But it's not just a straight line, kind of cut and plan. If you cut it off on a line.
Yeah. So the challenge here was figuring out how do we take that diagram geometry and wrap it around the sphere at the end. And the insight that solved the problem for us is recognizing that the diagonal diagrid is the complement of the orthogonal grid, which is obvious, of course, as soon as you say it. But once you recognize that the diagonal grid is the complement of the orthogonal grid, we can think about how you would trace an orthogonal grid on a sphere. So you would trace it the way we divide up our globe into latitude and longitude, meridians and parallels, is the analogous orthogonal grid for the sphere. So easy to take a conventional orthogonal grid on a cylinder and translate that into a meridian and parallel orthogonal grid on the sphere, and then take the diagonal complement of that. So what you're seeing with this converging helical grid on the end sphere is the complement of the meridian and parallel grid on that sphere. And that allowed us to converge. That allowed us to trace the end sphere and resolve the spherical ends of the cylinder.
So you guys always hear me say that everything you need to know about structural engineering you already know. You have an intuitive sense of how reciprocal frames work. If you've ever done this kind of thing, you can do it where everybody gets in a circle and sits. If you've ever gone to camp of any sort, everybody gets in a circle and sits down in each other's laps at the same time. So you have an intuitive sense of how this works. So this was just the fun lecture that we wanted to share with you guys. I think there was one or two boring ones that we were like, how are we going to round out this course? I think this was a better choice, and I think representation of complex geometry will be a really good one as well. That wraps up this lecture, which is great because our kids have lost patience and school starts for our 4-year-old in 15 minutes, and they're not
breakfast.
Well, I threw a croissant at them, but they're not dressed. So have a great day, guys.
Can I play on my tablet?
Yeah, we'll get you your tablet just